Welcome to the 34th lecture of the cont'd parallel algorithms. In the last class, we saw a couple of architectures that are very closely related to hypercubes. For example, the shuffle exchange graphs and the Bruin graphs we saw in the last class. Today, we shall see some use of them in simulating algorithms that are designed for hypercubes. In particular, we shall see normal hypercube algorithms first. An algorithm designed on HR, the r-dimensional hypercube, is called normal if every step of the algorithm involves messages along one dimension and two consecutive steps use adjacent dimensions. For example, if you consider H3 and if the dimensions are numbered 1, 2, 3, then the requirement is that every step should use any one of these three dimensions and two consecutive steps should use adjacent dimensions. For example, if the first step of the algorithm uses dimension 2, then all messages that are passed in the first step should be along the second dimension. Now, in the second step, the dimension used should be consecutive with 2, should be adjacent to 2, therefore, it should be either 1 or 3. So, let us say we choose 1 for the second step, then in the third step, the dimension used should be an adjacent 1. The adjacent dimension could be either 2 or 3, because adjacency also goes cyclically. So, the adjacencies are then defined in this fashion for a 3-dimensional hypercube. So, the next dimension could be 2 or 3, then for 3 it could be either 1 or 2 and so on. In particular, for a hypercube 4, the adjacencies are like this. Dimension 1 is adjacent to both 2 and 4, 2 is adjacent to 1 and 3, 3 is adjacent to 2 and 4, and 4 is adjacent to 3 and 1. So, one possible dimension sequence for a normal hypercube algorithm that runs on H4 would be 1, then 2, then back to 1, then 4, then 3, then 4 again, then 1, then forward to 2, then 3, then 4, 3 and so on. So, always we have plus or minus 1 on the dimension. When you go from one step to the next, the dimension either increases or decreases. When the dimension decreases from 1, it goes to 4. When the dimension increases from 4, it goes to 1. So, an algorithm which uses dimensions of this sort is called a normal algorithm. For example, when you consider a hypercube of 3 dimensions, edges of one particular dimension, this is the horizontal dimension here, these edges form a matching. Therefore, in a normal hypercube algorithm, the messages that are passed in any one particular step will be along a matching. Therefore, one message will involve only the source and the destination, and one node will be involved only with a couple of messages. One message is sends and one message is receives. So, now let us see how a normal hypercube algorithm can be simulated on a shuffle exchange graph. A normal algorithm on HR on a shuffle exchange graph of dimension r. Let us say the first step of the algorithm uses dimension k. The algorithm that is to be simulated has this property. Let us say the first step of the algorithm uses dimension k. In that case, if you consider a vertex u equals u1 through ur, in particular if I make the dimension k explicit, then this is what u is. U will be communicating with dimension k neighbor, the number of which will be identical to u at all positions other than the kth. So, u prime is the dimension k neighbor of u. These two should be communicating in the first step of the algorithm. Now, how do we ensure that these two communicate in the first step on a shuffle exchange graph? On a shuffle exchange graph, we will use the exchange edges for the actual communication. What we do is this: map this vertex to the vertex numbered of the shuffle exchange graph. That is, vertex u of HR is mapped to this vertex of the shuffle exchange graph. In that case, u prime will get mapped to this node of the shuffle exchange graph. You can see that these two vertices are adjacent, and they are adjacent along the exchange edge. What we find is that the dimension k edges of the hypercube are mapped to the exchange edges of the shuffle exchange graph. Therefore, all of them can now communicate in order one time. In other words, the first step of the algorithm is executed in one step. Now, let us come to the second step. The second step of the algorithm will use either dimension k plus 1 or dimension k minus 1. Suppose it uses dimension k minus 1. Suppose the second step uses dimension k minus 1. Then what we do is this: the process of vertex u is currently at this node of the shuffle exchange graph. Let us send it to this vertex instead. The process of vertex u is now sent to vertex uk plus 1 through ur and u1 through uk minus 1. Then the k minus 1 dimensional neighbor of u will be now the exchange neighbor of u in the shuffle exchange graph, or strictly speaking, the dimension k minus 1 neighbor of u in HR will be now at the exchange neighbor of u in SEGR. That is, u and its k minus 1 dimensional neighbor in HR will now be exchange neighbors in SEGR. That is, the process which corresponds to vertex u that was initially at this vertex has gone to this vertex now. Similarly, the process that corresponds to the k minus 1 dimensional neighbor of u, which is this is the k minus 1 dimensional neighbor of u. The process of this node in HR would have now reached the exchange neighbor of this vertex in the shuffle exchange graph. Therefore, the message passing between those two nodes, u and its k minus 1 dimensional neighbor in HR, can now be achieved in order one time, in one step. Then what is the total amount of time that we have taken for simulating the second step? One step is needed to send the process to the appropriate node, but we see that this vertex and this vertex are adjacent using a shuffle edge. So what is needed is that the process of u, which was at this vertex initially, has to move to this vertex, which happens to be a shuffle neighbor of this vertex. So that movement can be achieved using a shuffle edge. So the time taken for this repositioning of the process of vertex u of HR is order 1, is one step, and then another one step is needed for simulating the actual step. So we have taken a total of 2 steps for simulating the second step, and then continuing like this, we find that step 1 is simulated in one step. Step 2 requires the repositioning of the process, therefore we will take a total of 2 steps. Step 3 again uses an adjacent dimension, so the dimension would be either k or k minus 2. If the second step had used k minus 1, then it would take an additional 2 steps, and continuing like this. The last step of the algorithm, which let us say is the teeth step, again would take 2 steps. Therefore, the entire simulation would take 2t minus 1 steps. What this concludes is that SEGR can simulate an HR algorithm of t steps, that is, the algorithm takes t steps on HR in 2t minus 1 steps. So, SEGR is quite versatile indeed. Normal hypercube algorithms can be simulated on SEGR at double the time, nearly double the time. Now, let us prove that shuffle exchange graphs are universal as well. To show this, we consider an interconnection network of constant degree. So, let us call this network G, and an algorithm A designed on G. Say A takes order of t steps on G. Let us say we want to simulate this on a shuffle exchange graph. First, we will see how to simulate this on a hypercube using a normal algorithm. The simulation would be a normal algorithm, and then the normal simulation can be run on an SEG of the same dimension. So, we have a fixed interconnection network. This is like the simulation we had seen earlier. Let us edge color the graph G with delta plus 1 colors, where delta is the maximum vertex degree of G. Now that the graph is colored, consider each color class separately. So, each color class forms a matching. So, let us consider color class 1. Every other color class is identical. So, whatever we do for color class 1 can be replicated for the other color classes. So, when you look at the first color class, you find a matching of the sort in the network, and the messages have to be passed between these nodes. So, if this is node I, let us say this is node pi of I, a message has to be sent in this direction, and a message also may have to be sent in this direction. So, if you consider all these mappings, I to pi of I and pi of I to I, what we get is a permutation of the vertices. That is, for every vertex we have a destination for the message which is originating at that vertex. So, this essentially specifies a permutation pi. That is, the messages which are present at the sources have to be permuted and sent to the destinations. So, the message which is at I has to be sent to pi of I for every I. This is what is to be achieved for color class 1, and once we manage this, we can do the same thing for every single color class. Now, suppose we had a Benesch network. We know that in a Benesch network, there are node disjoint edges, node disjoint paths connecting for every I the ith vertex in the first column or the 0th column to the pi-ith vertex in the 2rth column for every permutation pi of the inputs. So, we will use this property of a Benesch network. So, if we had a Benesch network and if we were permuting the packets using a Benesch network, then all we would have to do would be to line up the messages at the 0th column. This is the 0th column. So, we will line up the messages at the 0th column and then send the messages through the Benesch network in lockstep, in the sense that at any particular time all the messages will be in the same column. That is, after t steps all of them will be in the tth column. So, after 2r steps all of them would be coming out at the right end in the appropriately permuted form. That is if we had a Benesch network, but we do not have a Benesch network. But let us assume that we have a hypercube of the same dimension. But how can a hypercube simulate a Benesch network? Recall that if we contract every single row of a Benesch network, or a butterfly for that matter, a Benesch network is nothing but two butterfly pasted back to back. So, if you contract an entire row of a Benesch network into a single vertex, then we get a hypercube. And then if you run a Benesch network algorithm which pulses the data through the Benesch network in a lockstep manner in such a way that all the messages are lined up in a column in every single step, then you find that if you run it on a hypercube, in every step each node of the hypercube has exactly one message. And in every step edges of exactly one dimension are used. That is because in every step the messages are passing from one column of a Benesch network to the adjacent one. When these are collapsed, these edges will all correspond to edges along a particular dimension of the hypercube. So, what we find is that the permutation that we achieve using a Benesch network can in fact be achieved also using a hypercube. But then this hypercube algorithm, this simulation in fact turns out to be a normal algorithm. This simulation is a normal algorithm and runs in 2R steps, but 2R is nothing but 2 log n. So, this algorithm runs in 2 log n steps at the most, but we have already seen that an algorithm which runs in a normal algorithm that runs in t steps on a hypercube can be simulated on a shuffle exchange graph of the same dimensions in 2t minus 1 steps. Therefore, this would take at most 4 log n steps to ignore the smaller order terms on a shuffle exchange graph of the same dimensions, which is log n. So, what we find is that one single step can be simulated in order of log n time in a shuffle exchange graph. But this is only one of the steps, that is, we considered only one color class, but since the interconnection network had d color classes, simulating all these color classes would take order of d log n time on shuffle exchange graph of dimensions log n. Therefore, algorithm A that runs in order of t steps on our general constant degree interconnection network G can be simulated on an SEG of dimensions log n. An SEG of dimensions log n and G have the same number of vertices. So, we are essentially considering an SEG of the same number of vertices. The simulation takes order of t log n time, which means a shuffle exchange graph is capable of simulating any general interconnection network of constant degree with an order log n factor overhead. This establishes the universality of the model shuffle exchange graphs. Whatever you do on a shuffle exchange graph can also be done on a De Bruijn graph, because of as we saw in the last class, the De Bruijn graph is a minor modification of a shuffle exchange graph. The two can simulate each other with a constant overhead. Therefore, these two models are universal indeed. With that, we come to the end of our discussion on interconnection network algorithms. Now, we are going back to PRAMs and let us explore some limits to parallelization. When do we say that a problem is parallelizable? So, we use this following definition. A problem we say is parallelizable if there exists a PRAM algorithm for that problem. The variant of PRAM is of no relevance, that runs in polylogarithmic time using a polynomial number of processors in problem size n. What it means is this: say for problem P, there is an algorithm that runs in order of log n to the power k1 time. So, here k1 is a constant, it is independent of n, When we say that it is a constant, what we mean is that it is independent of n using n power k2 processors, where k2 is order of 1 again, it is a constant independent of n on any PRAM. Now, this definition is independent of the variant of the PRAM. That is because all models of PRAMs can simulate each other in polylogarithmic time using a polynomial number of processors. That is, even if you have an algorithm that runs on a priority CRCW PRAM, it can be simulated on an ER-EW PRAM using a polynomial number of processors in polylogarithmic time. All you have to do is to sort the processors on the address of the location that they want to write to, and then the conflict resolution can be achieved by finding the least process that wants to write in each memory location. The details I leave to you as an exercise, but then you will find that the algorithm runs in order of log squared and time extra factor. That is, if the original algorithm ran in log of n power k1, then the simulation would run in order of log n power k plus 2, which again is polylogarithmic using a polynomial number of processors. Therefore, this definition is independent of the variant of the PRAM. If this holds on any one variant of the PRAM, it will hold on another variant of the PRAM. Therefore, if a problem is parallelizable on one variant of the PRAM, it is parallelizable on any other variant in this sense. So, this is, let us say, our definition of parallelizability. Now, let us see what are the consequences of this definition. There is this complexity class P that you are all familiar with. P is the class of all languages that can be recognized by deterministic Turing machines that are polynomial time bounded. In other words, these are the problems that can be solved in polynomial amount of time. So, we are considering only the language recognition problems. So, P is the class of all such languages. Now, we know that P is model invariant, exactly as we spoke about the variance of PRAMs. We can also consider the variance of models of computations. For example, Turing machines and random access machines and various other models of computation that have been proposed can simulate each other in polynomial time. Therefore, what you manage to do on one model can be done on the other model in polynomial time as well. That is why we see that P is model invariant, exactly the way that our notion of parallelizability is independent of the PRAM invariant. Now, let us define the complexity class NC, which is short for Nick's class after Nick Pippenger. We define NC as the class of all languages L such that for every input W of length L, L can be recognized by a PRAM algorithm. As I said before, the variant of the PRAM algorithm is irrelevant. This PRAM algorithm should run in order of log n power k1 time using n power k2 processors for k1 and k2 that are order 1. That is, k1 and k2 are independent of n. All languages of this sort belong to the complexity class NC. Now, what can we say about NC and P now? It is obvious that NC is a subset of P. That is because any NC algorithm In other words, an algorithm that runs in polylogarithmic time using a polynomial number of processors is an NC algorithm. It witnesses the membership of some language in NC. So, any NC algorithm can be simulated on a single processor machine, which is a random access machine, in polynomial time. For example, if an algorithm runs in order of log n power k1 time using n power k2 processors, then the cost of this algorithm is n power k2 times log of n power k1, which happens to be order of n power k plus 2, k2 plus 1, which is a polynomial. Therefore, any algorithm in NC is, any problem in NC is also in P, or in other words, NC is a subset of P. But then, does the converse hold? Is P a subset of NC? Or in other words, is NC a proper subset of P? This is a question to which we do not have an answer yet. This is analogous to the P equal to NP question. This question is still open. Similarly, the question whether P is a subset of NC is still open. We shall define a class of problems which we call the P-complete problems for NC reductions. The class of P-complete problems consists of the P problems that are hardest to parallelize. That is, we will be able to parallelize them only if NC equal to P. So, if P is not equal to NC, then there are some P problems which are not parallelizable, and then the P-complete problems would indeed be not parallelizable. So, what do I mean by NC reductions? Let me define the reducibility. We say that L1 is NC reducible to L2, which we denote as in this manner. So, you can imagine that L1 has been reduced to L2. So, you must be clear about the order of this inequality. L1 is reducible to L2 means L2 is the harder problem. So, L1 is NC reducible to L2 if there exists an NC algorithm. As I said before, an NC algorithm is one which runs in polylogarithmic time using a polynomial number of processors. There exists an NC algorithm that transforms an input U1 to L1, that is, we are given a string U1 and we want to check whether U1 belongs to L1, into an input U2 to L2, so that U1 belongs to L1 if and only if U2 belongs to L2. If this is the case, then we say that L1 is NC reducible to L2. So, there must exist an NC algorithm, which is the reducer. So, there is a reducing algorithm. So, this is a reducing algorithm. Let me denote that by AR. This is a reducing algorithm which takes an input U1. This is an input for L1, that is, we want to decide whether U1 belongs to L1 or not, and then what it produces is U2, which is an input to L2, and this translation of U1 into U2 will take polylogarithmic time using a polynomial number of processors. And what we know is that U1 belongs to L1 if and only if U2 belongs to L2. So, the translation is so that U1 belongs to L1 if and only if U2 belongs to L2. What this entails is that if L1 is NC reducible to L2 and L2 belongs to NC, then L1 also belongs to NC. Why is this? Let us say we want to construct a recognizer for L2, for L1. What we have is a recognizer for L2. Let us say L2 belongs to NC. So L2 has an algorithm A which runs in polylogarithmic time using a polynomial number of processors. And then we have this reducer AR, and let us say we are given an input U1. AR produces an output U2. What we know is that U1 belongs to L1 if and only if U2 belongs to L2. The question that is posed to us is this: does U1 belongs to L1? Does U1 belong to an L1? Then the translator ensures that U2 is in L2 if and only if U1 belongs to L1. But we have a decider for U2. We have a decider for language L2. So if U2 is fed to that, it will produce either yes or no, depending on whether U2 belongs to L2 or not. So the membership of U2 in L2 can be tested in polylogarithmic time using a polynomial number of processors. So let us say this takes n power k1 processors and order of log n power k2 time, and let us say AR takes n power L1 processors and order of log n power L2 time. Then when you juxtapose these two algorithms and use the larger of the number of processors, then we find that using a polynomial number of processors in polylogarithmic time, you will be able to execute this. In other words, the language L1 belongs to NC. It is also obvious that NC reducibility is transitive. If L1 NC reduces to L2 and L2 NC reduces to L3, by juxtaposing the two reducers, we find that L1 NC reduces to N3. So NC reducibility is transitive as well. Now we say that L is P complete for NC reductions if every P problem NC reduces to L. If L has an NC algorithm, that is, if L belongs to NC, then P is a subset of NC. That is because every P problem NC reduces to L, and if L had an NC algorithm, then every problem in P would have an NC algorithm. So to reduce every P problem to NC, to prove that a problem in P is parallelizable, all we have to do is to crack one of the P complete problems in NC. Once we do that, every P problem has a parallel solution. But then these definitions are all fine, but just because we define a term does not mean that it applies to any actual object. That is, we do not know whether there exists an there exists a language which is P complete for NC reductions yet. So that is the next question: is there a language L that is P complete for NC reductions? We shall show that the circuit value problem is P complete for NC reductions, and once we show that one language is P complete for NC reductions, we can show that several other languages are P complete for NC reductions as well by reduction to this language. So this language we shall define in the next class and show that is P complete for NC reductions, and then we shall show several other languages to be P complete for NC reductions by establishing NC reduction from the circuit value problem to those. So that is it from this lecture today. Hope to see you in the next. Thank you.